If you're happy and you know it, clap your hands. If you're happy and you know it, clap your hands. If you're happy and you know it, 'cause you love to use exponents. If you're happy and you know it, clap your hands. Hello, my dears. Welcome to our second class of Unit 6. I hope you were clapping at home. I would have joined you, of course, but I have no hands. I'm just a disembodied voice floating in the ether and incapable of clapping. And perhaps even more importantly, nothing makes me happy because my heart is cold and dead and unable to feel joy. Anyway, today, with a working understanding, hopefully, of how both exponents and radicals do what it is that they do, for the time being, we're going to put our radicals on the back burner and dive deep into exponents by discovering what we'll call the laws of exponents. There are 8 of them in total for us to talk about, each of which you'll see we're going to motivate with a guiding question. And one of them you'll find we've actually already stated. Last video was super long. This time I'm going to try and get you out of here in about 10 minutes. Can I do it? Let's find out. In general, we're going to use symbols to represent each of these laws. The symbols that we use are as follows. In an exponent, there's a base, the thing being exponented, and the exponent itself. The bases we will typically, by convention, represent using the variables a and b that will get swapped out for specific numbers depending on the problem we're working with. Same thing for the exponents. We're going to use symbols to represent our exponents. They'll get replaced by specific values. The symbols that we use are m and n. Using these symbols, we want to see how we can represent the general case for what happens for something like our first question, which is, well, what happens if I take a base and raise it to an exponent that's a fraction? Well, we already know our first law of exponents. What happens here? Take each of these expressions, rewrite them as something that makes it more obvious of what I'm trying to do, and once you've got it, try and simplify them. Go, go. And stop. I know from last time that if I have a denominator of a fraction, what that really tells me is that that number is becoming the index of a radical. So 125 to the power of 1 over 3, the 3 becomes the index. I'm taking the cube root of 125. I want a number that multiplies by itself 3 times to get to 125. That number is positive 5, right? Because 5 times 5 times 5 is equal to 125. Same thing for 49 to the power of 1 over 2. That 2 in the denominator of the fraction becomes the index. I am taking the square root of 49. Well, I know that there are 2 answers to this question. 7 times 7 gives me 49. So does negative 7 times negative 7. So plus or minus 7 is my answer to this question. Now let's get a taste of that symbolic representation. We'll write our first law of exponents as follows. If I take any number, we'll call it a, and I raise it to the power 1 over some number n, well, I know here that every fractional exponent is a radical in disguise. That denominator of n becomes the index of our radical, whereas the base a becomes the radicand of our radical. Cool. So we've talked about fractional exponents, but an exponent could be any kind of number. We've talked about positive exponents, but what happens if the exponent for our second and third laws is negative? Or maybe, what if that exponent is neither positive or negative, but 0? This will give us our second and third laws of exponents. I want to see what happens if my exponent is 0 or if my exponent is a negative number. Something like negative 38 raised to the power of 0. What's that? Something like 5 to the power of negative 2. What's that? I have no idea. And that's good. We're going to figure this out together. But before we do, I want you to take a guess. Even better if that guess is wrong. Make a conjecture about what you think might happen in each of these cases. And then once you've got an idea, we'll come back and see if that idea has some weight. Go, go. Alrighty, let me give you a visual representation of how this is going to make sense. I'm going to use powers of 2 because those are nice and friendly and relatively easy to work with. I'll start here in the middle at 2 to the power of 1. 2 to the first power really just means I need 1 copy of 2. Well, that's just 2. And then 2 squared, I know, is 4, followed by 8 for 2 to the third, 16 to the power of 4, right, or 2 to the power of 4, and so on and so forth. Well, what do I do every time that I go up a power? Well, hopefully this is obvious to us from what we know about exponents. If I want to go up from 2 to the first to 2 to the second, I need another copy of 2 multiplying. So I'm just adding in another copy of the base. To get from 4 to 8, right, I need to multiply by another copy of 2. Same thing to get from 8 to 16. Well, now I want to think about what would happen if I need to go down a power. What would I do if I want to move backwards from 16 to 8, or 8 to 4, or 4 to 2? What's going to happen here? 5, 4, 3, 2, 1. Well, hopefully you've got this idea. If I need to move up a power, I multiply by a copy of 2. If I'm taking away a copy, moving down a power, I need to instead move backwards by dividing by a copy of 2. 16 divided by 2 gets me to 8. Divide by another 2 to bring myself back down to 4. Divide by another 2 to bring myself back down to 2. Well, if we follow this pattern again, what should the value of 2 to the power of 0 be? 5 seconds, go. 4, 3, 2, 1. Well, if I follow this pattern, to get up from 2 to the 0 to 2 to the first power, I'd need to multiply by 2. To get back down, I should need to divide by a copy of 2. So 2, my previous exponent value, divided by a copy of 2, tells me that 2 to the power of 0 should be equal to 1. This is, in fact, our second law of exponents. It says that if I take any number, we'll call it a, and I raise it to the power of 0, no matter what the value of a is, this exponent will always work out to 1. With this idea in mind, simplify your next two. Negative 38 to the power of 0, negative 7 to the power of 0. What are each of these going to work out to? Go, 30 seconds. 5, 4, 3, 2, 1. Well, negative 38, the base is negative 38. Anything raised to the power of 0 is 1. But for negative 7 to the power of 0, remember that this is an order of operations question in disguise. A negative sign in front of something means negative 1 times the thing. 7 to the power of 0, anything to the power of 0 is 1. So I have negative 1 times 1. This guy works out to negative 1. Lovely! We now know the second law of exponents. Let's figure out what happens with the third one. If I want to continue going down powers, now I want to get down from 0 to negative 1. Well, again, what should I do if I want to go down a power? Well, I've seen that every time I move down a power, I'm dividing by another copy of the base. So here, if my base is starting at 1 and I'm dividing by a copy of 2, 1 divided by 2 tells me that 2 to the power of negative 1 should be equal to 1/2. Dividing by another copy of 2, I could keep going. Well, dividing by 2 is the same as multiplying by 1/2. So my next guy, 2 to the negative 2, should be 1/4, followed by 1/8, followed by 1/16, and so on and so forth. Well, I want to be a little bit annoying here. Let's rewrite each of these as fractions. Or not as fractions, sorry, but exponents. 1/2. If I want to be really annoying, I could write 2 as 2 to the power of 1. I hope you agree with me. If I take 4 and rewrite it as a power of 2, well, 4 is the same as 2 squared. And I could keep going. 1/8, this is the same as 1/2 to the third. And then 1/16 is 1/2 to the fourth. What do you notice here about the negative exponent and the fraction that that negative exponent creates? 5 seconds. What do you see? 4, 3, 2, 1. Well, hopefully you'll notice that the exponent that was negative, right, it goes into the denominator of the fraction and the negative sign goes away, right? The negative 2 over here became a positive 2 in the denominator of my fraction. So what we'll say for our third law of exponents, making observations about that pattern, is as follows. If I take some number a and I raise it to the power of negative n, what's going to happen here is that this is going to become a fraction where the numerator is 1, the denominator, the negative sign in our exponent goes away, and we're just left with a to the power of n. By the way, what did I really just find here? What does 1 over something? That's a fancy way of representing an idea in math. What did we really just find here? All right, maybe you're familiar with this idea, but if I take 1 over something, right, 2 and 1 over 2, for example, they are reciprocals of each other. So, really, what a negative exponent tells me to do is to take the reciprocal of the positive version of the exponent. So here, for 5 to the negative second power, what I want to do is find the reciprocal of 5 to the second power. So 1 over 5 to the second power. And I can simplify that, right? 5 to the second power is 25. Same thing here for 2/3 to the power of negative 1. Again, this is really telling me to find the reciprocal of the base. Well, the reciprocal of 2/3 is 3/2. Cool! So with that, you've now discovered your second and your third law of exponents. I know I'm a little over 10 minutes, I promise, but let's just do a little bit of practice to make sure we feel okay. Here you go. Using what you've just discovered, you've got 6 statements. Let's find their values. Go, go, go. And stop. For our first one, I have negative 365 raised to the power of 0. No matter what, anything raised to the 0 power is 1. Negative 29 to the 0 power, though, we know that this guy's a little bit different. This, of course, is an order of operations problem. This means negative 1 times 29 to the power of 0. 29 to the power of 0 is still 1, as is anything raised to the power of 0. Negative 1 times 1 gives me negative 1. X to the power of negative 7. Well, that's the reciprocal of x to the 7th. So 1 over x to the 7th is my final answer. Same thing here, 3 to the power of negative 3. I want the reciprocal of 3 to the 3rd power. Well, 1 over 3 to the 3rd I can simplify. 3 to the power of 3 is equal to 27. Second to last, 4/7 to the negative 1st power. Again, a negative exponent is just telling me to take the reciprocal. The exponent of 1 won't change the 4/7, so I just want the reciprocal of 4/7, which is 7/4. And then finally, I can get real annoying with it. 6y to the power of 0 times 3 to the negative 2. Well, 6y to the power of 0. 6 is the what of y to the 0 here? 5, 4, 3, 2, 1. Hopefully you remember here, it's joined to y to the 0 by multiplication. It's the coefficient of this y to the 0. So this, again, is an order of operations problem in disguise. 6y to the 0 is not 1. It is 6 times y to the 0. There's that invisible multiplication sign there. And from here, I can simplify. Well, I have 6 times y to the 0. Anything to the power of 0 is 1. And then I have 3 to the power of negative 2. Well, that's 1 over 3 squared. So I really have 6 times 1, which is 6, times 1 over 3 squared, which is 1/9. Now if I want to multiply 6 times 1/9, make 6 into a fraction. 6 over 1 times 1 over 9 gives me 6 over 9, which reduces to 2/3. There's the idea behind these laws of exponents. We can take something really complicated and seemingly scary like that first expression in f and show, using the laws of exponents, that it can be simplified to something nice and friendly like 2/3.